Okay. So I was saying, when we are now talking about resistances and the like, what we're talking about is what the manufacturers use when manufacturing resistors, I mean. So they choose a material so that they have control over the resistivity. Then they choose the cross-sectional area so that they have the control over of the length. And then they choose the gauge of the wire so that they have control of the control. Excuse me. Hello, hello. Can you mute your audio, please? Can you mute your audio so that we don't disturb? So I was saying the parameters which we're talking about are what the manufacturers use when they are manufacturing resistors, right? So when you come now to Ohm's law, we are trying to see then how do we use these resistances to calculate quantities in the circuits. Remember, we said in a circuit, you might need to calculate the voltage across an element, the current through an element, or you might have also to calculate the power dissipated in an element. And this is when these laws now come into play, right? So the first law that we talk about now will be Ohm's law. So the Ohm was identified as the unit of resistance named after George Ohm. We talked about that, right? So this Ohm guy was a physicist, and then we now know of Ohm's law, right? So the law given by Ohm implies that the current flowing in a conductor is directly proportional to the potential difference across the conductor, that is the voltage across the conductor, but also inversely proportional to the current, to the resistance of that material. Right, so that is Ohm's law stated in general. It shows the direct relationship between current and voltage and the inverse relationship between current and resistance. So that is the picture of George Ohm, which I found in a later stage. So the law states that the current flowing through a conductor is inversely proportional to its resistance. That is, if the potential difference across it is constant. So when I'm talking about proportionality, remember there should be a proportionality constant. So when you say the current is inversely proportional to resistance, we are now saying there's a proportionality constant in form of the voltage at a given temperature. So in general, effect is called cause over opposition, and in our case, effect is the current, voltage is the cause, and opposition will be the resistance. So commonly stated, Ohm's law is stated as V is equal to IR. Voltage is equal to current times resistance, right? And I've talked about that. So we have to remember that we said in circuit analysis, we find voltage across a material, current through the component, or the power absorbed or generated or converted by the element. So Ohm's law is the basic law in circuit analysis, and all other laws are extensions of these laws. So realize that when you talk about any other laws, you can directly link them to Ohm's law. You can directly link them to Ohm's law. right? So to apply Ohm's law, it is important to take note of the direction of the current and the polarities of the voltages. So remember we said for passive elements, current will flow from a higher potential to a lower potential. And for active components, current will flow from a lower potential to a higher potential, and hence given a negative value. So the value of resistance can be between 0 and infinity, where a path of 0 resistance is our short circuit, and the path of infinity resistance is the open circuit, right? So when the path has 0 resistance, it's a short circuit and it has 0 voltage across it. When a path has infinity resistance, it has no current flowing through it and the maximum voltage determined by the source, right? So let's take, for example, where we can use Ohm's law. If a heater draws 6 amps of current when the voltage across is 240 volts, what is its resistance, right? So from V is equal to IR, we are saying 240 is equal to 6 times R. R will be the resistance, and you find out that the resistance of that heater is 40 ohms. Now, what is the power dissipated in that resistance now? Since V is equal to IR, P is equal to IR, which is V multiplied by R. From P is equal to VI. And hence, P is given as I squared R in watts. So the power dissipated in a resistive element is equal to the square of the current multiplied by their resistance. So in that case, from the example above, we can substitute the values of current and resistance to get watts. So that heater can also be termed a 1.44 kilowatt heater as shown in the example, right? In another example, for the circuit below, calculate the current through the resistance and the conductance of the resistor and the power dissipated by the resistor. So we are now putting everything that we're talking about into an electrical circuit, which will be the main component that we have to deal with. So this is our voltage source of 30 volts. The current flowing through there is given as I, and our resistance is 5 kilo ohms. So calculate the current through the resistance. If V is equal to IR, it means I is equal to V over R, and you calculate your current is 6 milliamps. Milliamps, because we have 0.006, remember milli, it means divided by what? Divided by 100. So you can write 6 milliamps or 0.006 amps. Both are still correct. And the solutions, in most cases, I want them given in 3 significant figures for our calculations. Then conductance is called the inverse of resistance. So if G is got 1 over R, you know your R has got 5 kilo, which is 5,000, and then you get your conductance 0.002 Siemens or 2 millisiemens. Then power dissipated becomes called I squared R. We've calculated our I is 0.006, so squared multiplied by the resistance, which is 5,000, you get 180 milliwatts as the power dissipated in that resistor. So this is a very simple example of an electrical circuit where you have to do those calculations using Ohm's law. Right. I hope everything is clear up to now. Right. So, circuit configurations. The first configurations is a series circuit. So, a series circuit is a circuit in which the components are connected in a chain without a branch in between, and they share only one connecting point. or a node. And for a series circuit, the same current flows through all the elements that are in series. So that is an example of a series circuit. You can see that these two have one connecting point, which is one node there in common. These two also have one node in common. These two have one node in common. And hence we can say they are in series. And the same current flows through those components. So if you calculate the current through R1, you will know the current through the other components is still the same current since they are in series. So it is also important for you to know how to identify a series circuit. Now, so the total resistance of a series circuit is the sum of all resistors that are in series. So R is equal to the sum of all those resistors. So in this example, for 3 resistances, then our equivalence will be R1 plus R2 plus R3. So when you are now using Ohm's law, you have to bunch up all resistances that are in series into one equivalent resistance. Then you can calculate anything that is needed. So let's do that by way of an example. The circuit shows the series combination of resistors. Calculate the current drawn from the source and then determine the power dissipated in the 10 ohm resistor. So what is given there is a series circuit with a 65, 84, 73, and 10 ohm resistors in series. So you go back to your question after seeing what has been asked. From the circuit shows a series combination of resistors. Calculate the current drawn from the source and then determine the power dissipated in the 10 ohm resistor. So our focus now will be on the 10 ohm resistor. But before that, we need to calculate the current drawn from the source. So remember, from V is equal to R, it means we have to find the total resistance of this circuit first. So the total resistance will be the sum of these 4 resistances, that's 232 ohms. Then we can now use Ohm's law, where now the current will be the current flowing in that direction. So from V is equal to R, I is equals 25, which is our source voltage, divided by 232, which is our equivalent resistance. And you get about 1.08 milliamps as our resistance. But since you use it later, you can take this one and take note of the intermediate calculation, right? Then after that, now we have known the current drawn from the source. We now need the power dissipated in the 10 ohm resistor. Now these components are in series. So what it simply means is that they have the same current flowing through them. So it means this current through this and that is still 0.1077586 amps. So the power dissipated now is the value of this resistance, which is our interest, times I squared. So it's I squared times 10, and you get your 1.1, your 116 milliwatts as your power dissipated in that resistor. So that is how you apply Ohm's law for a series circuit. So in the series circuits, again, we have a law which is called Kirchoffs Voltage Law. We have Kirchoffs Voltage Law. So Kirchoffs Voltage Law now is based on the principle of conservation of energy, and it states that the algebraic sum of all voltages around a closed path or a loop is 0. In other words, we are saying the sum of voltage rises in a closed loop is equal to the sum of voltage drops in the same loop. So, in other words, we are saying the sum of all voltages, that is the rises and the drops, should be equal to 0 in a closed loop, right? So we can say the sum from M is equal to 1 to M of voltages, Vm is equal to 0. M will be the number of voltages in the loop, and Vm is the M M is the mth voltage. So in this question, voltage rises have a positive sign and voltage drops have a negative sign. So what will be our voltage rise? Remember, that will be the voltage on an active component. Voltage drops will be the voltages on the passive components. So the sum of rises should be equal to the sum of drops. So in the alternate equation, drops and rises have positive signs since they are in different sides of the equation. So if you say V rise is equal to V drops, they will be of the same sign. But then if you put them together, you are saying V rise minus V drop should be equal to 0. So that is Kirchoffs voltage law, right? So what is a closed loop? So a closed loop is a path in which you move around and you pass through a component only once, right? So if you move and pass through a component only once and come back to where you started, you have completed a closed loop in the circuit. So that is a closed loop in our circuit. So this is a closed loop, right? Another one, this one is also a closed loop. Then this one again is a closed loop. Also, this one on its own is also a closed loop. Because there's no branching, you are moving through a component once, then you are forming a closed loop, right? So as an example, the figure shows a series circuit using Ohm's law proof that Kirchoffs voltage law holds for the circuit. Right. So that is the circuit you have. It's a series circuit, 5 kilo ohm, 10 kilo ohm, and 7.5 kilo ohm resistors are in series. Then they are all supplied by a 45 volt source. So for us to use Ohm's law, remember Ohm's law says V is equal to IR. So we have to find the value of I and the value of V, and then the value of R. But V is given as 45. So we need the value of R, which is the sum of these three resistors, because they're in series. It gives you 22.5 kilo ohms. Then I, which will be the current flowing in that circuit, will be equal to the voltage divided by the total resistance in that 2 milliamps. So voltage across R1, VI is equal to IR, becomes equal to 10 volts. Voltage across R2 is equal to 20 volts. Voltage across R3 is equal to 15 volts. So the sum of voltage rises should be equal to the sum of voltage drops. So I'm moving from a negative to a positive, so this is a rise. Then from here, I'm moving from a positive to a negative, it's a drop. Here, something is a drop, and that is the drop. So we have 1 voltage rise and 3 voltage drops. So 45 becomes equal to the sum of the drops on that side, and you see that the equation comes out correct. And hence, we can say that Kirchoffs voltage law holds for that circuit. So those are some of the simple examples that we have in our circuit calculations. Right. The right hand side is equal to the left hand side. The right hand side is equal to the left hand side, and hence we can say right. Then there's also the voltage divider rule, which again applies to series circuits. The voltage divider rule, which applies to series circuits. So the voltage divider rule states that if resistors are in series and connected to a voltage source, they share the voltage across them in proportion to their values. So that means the larger resistor has a larger voltage drop across it, the smaller resistor has a smaller voltage drop across it. So that is what it means when we say they share the voltage across them in proportion to their values, their resistances. These windows are coming up everywhere. So mathematically, we can say the voltage across an element or across a series combination of elements in a series circuit is called the resistance of the element of the series combination divided by the total resistance of the circuit. So in other words, the voltage across element N or Rn will be equal to the value of Rn divided by the total resistance multiplied by the supply voltage. So we can still come back to our example and say we have R1, R2, and R3. So calculate the total resistance of the circuit, which we found to be 22.5. So voltage across R1 becomes equal to this resistance over the total resistance multiplied by the supply voltage, and you get your 10 volts. Do the same for R2, 20 volts, for R3, 15 volts. Right. So this also confirms Ohm's law. That means if you calculate the total resistance, then you use V is equal to IR for each component, you should get the same values of the voltages across those components. So in conclusion, we can say the resistance of a conductor depends on its dimensions, material, and temperature. Ohm's law relates current to resistance through voltage. Kirchoffs law is based on conservation of energy, that is Kirchoffs Voltage Law. Then the voltage divider rule enables the calculation of voltage across resistance without using the current. And this is the end of our lecture for today. Then tomorrow we'll look at the next lecture. Right, back to us. Do we have any issues or questions that we might need to be attended to before we end the lecture? You can unmute when you are now asking your question. I think I have a few minutes left. Yes, any questions? From the looks of things, you are still digesting. Let me save it and send it on YouTube, then you can revise whatever I talked about. Thanks for your time. Until we meet tomorrow.
Thank you very much.
Right, we'll try to at least start around 9 o'clock. By 10, we should be done tomorrow. Are we okay?
Okay, thank you.
Thank you, sir.
Thank you, sir.
I think Zoom is the best.
Thank you, sir.
All right, guys.
Okay, thank you, sir.
So that we
Thank you.
Bye for now.